seconds for a pressurized steel vessel to tear itself apart. What you're seeing is a Bleve. That stands for Boiling Liquid Expanding Vapor Explosion. In the process industries, it is considered a worst-case scenario. When a storage tank is exposed to intense heat, the massive energy stored inside can be unleashed with devastating force. A static storage tank effectively becomes an enormous bomb. Preventing that transformation requires a precise understanding of the physics that trigger the explosion. The threat begins with a rapid phase transition. When pressure drops, the high-temperature liquid inside flashes instantly into gas. This sudden shift requires massive space. The expanding vapor pushes outward, generating incredible mechanical force. Because we often see huge fireballs in these videos, it is easy to assume the explosion is caused by the chemical igniting, but the blast itself is an entirely physical event. A Bleve can happen with water or liquid nitrogen just as easily as with propane. Fire is usually the external trigger that starts the process, but recognizing that the explosion is an issue of mechanical pressure allows engineers to target the structural vulnerabilities of the tank itself. The countdown to a rupture follows a predictable 6-step sequence. It almost always begins with an external fire, like a pool of burning fuel or a high-pressure jet flame, impinging directly on the outside of the container. The fire's thermal energy penetrates the steel, rapidly raising the temperature of the liquid inside well past its normal boiling point. As the liquid boils, vapor builds up at the top of the tank. The internal pressure spikes. Most tanks are equipped with a pressure relief valve, which opens to vent this excess gas and keep the pressure stabilized. But the relief valve cannot solve the underlying problem of the external heat. The steel wall itself weakens under the extreme temperature, losing its structural strength until a fracture begins to form. The thinned, overheated metals simply cannot contain the immense internal pressure anymore. The tank tears completely open. With the pressure suddenly gone, the remaining superheated liquid aerosolizes in a fraction of a second. It expands violently into the atmosphere as a dense mist. Because this sequence requires time to build, engineers have specific identifiable windows to intervene and stop the pressure from reaching the breaking point. When the tank fails, the explosion propels massive, jagged pieces of steel outward at high velocities. These missiles tear through nearby infrastructure, causing severe damage. If the escaping vapor cloud is made of a flammable chemical, it will ignite. The resulting fireball generates an intense wave of thermal radiation that scorches everything in its line of sight. Those flying shrapnel pieces and the extreme heat wave then strike adjacent storage tanks, rupturing their pipes and sparking new fires. This is why a Bleve is rarely an isolated incident. The explosion creates a domino effect of plant-wide destruction, multiplying the danger with every nearby vessel it compromises. To stop this chain reaction, facilities rely on active cooling. Automated water deluge systems immediately drench the outside of the tank, stripping away the thermal energy and stopping the pressure spike before it starts. That active defense is built on top of strong baseline engineering. Tanks must be constructed from high-strength alloys and rated for extreme pressures to buy enough time for cooling systems to work. The pressure relief valves must also be perfectly calibrated and kept in working order. This requires rigorous, fully documented inspection routines to catch corrosion or mechanical faults before a crisis. Physical layout is just as important. By maintaining strict safety distances, clear exclusion zones, and thick blast walls, a fire at one tank is physically isolated from the rest of the farm. No single measure guarantees safety. Real hazard prevention relies on this layered network of physical and mechanical controls to neutralize both the thermal and the pressure threats. Beyond the hardware, survival comes down to human preparedness. Facility operators need comprehensive evacuation plans and the training to respond to alarms rapidly and decisively. The sequence of a boiling liquid explosion is destructive, but it is entirely governed by predictable physics and preceded by clear warning signs. By combining an absolute respect for the mechanics of rapid depressurization with strict maintenance of layered barrier systems, we can keep these pressures contained, secure the facility, and save lives.